So this time we're going to draw the sheet silicate mineral structure. This is another group of minerals, the sheet silicates, and they're characterized by having silica tetrahedra linked together not just in chains but in two directions to form a sheet of strongly bonded silica tetrahedra. So I'm starting here by drawing a single chain of silica tetrahedra. Then we're going to build onto that. I'm leaving off those 3 lines in the middle again, just to have it go more quickly. And that's the basic double chain structure that we saw in the previous clip. Now we're going to just keep adding on in the vertical direction. We're going to keep this building to make a 2-dimensional sheet of silica tetrahedra. Let's see, let's draw one more row maybe. Like so. Okay, I think you get the picture. The chain silicates, they had the linkage between the silica tetrahedra just in one direction or one dimension, but the sheet silicates, the structure keeps building in 2 directions or dimensions in the mineral. Now, we have to remember that up above the plane of the slide or the sheet, we have another oxygen up here above the plane where all the tetrahedra are strongly bonded. And all the other oxygens in this tetrahedron are shared with 2 or between 2 adjacent tetrahedra. So these 1, 2, 3 oxygens at the corners of the triangular base are completely satisfied and don't need to bond with anything else. They have their 2 electrons, they're happy. But the one that's above the plane of the sheet, that needs another electron. So we're going to have in the 3rd dimension, up here, if you will, we're going to have bridging cations again that are more weakly bonded by ionic bonds compared to the stronger, partly covalent bonds within the sheets. So these sheet silicate minerals have one direction of cleavage along the zone of weak bonding where the bridging cations are, and the bridging cations in these sheet silicate minerals are going to serve as bridges between sheets, kind of like, I don't know, peanut butter inside a peanut butter sandwich, where the silica tetrahedra sheets are the bread of the sandwich. And those ionic bonds are weaker, so these minerals tend to cleave in one direction, parallel to the silicate sheets. So let's talk about some examples of sheet silicate minerals. We have the minerals like the micas, and there are 2 common ones, Biotite Mica and Muscovite Mica. And then there's also a whole big group of minerals called the clay minerals, or just clays. And those clay minerals, they come in really tiny grains. Very, very small, less than 1/256th of a millimeter across, so that's pretty darn small. So they tend to show up in rocks or in soils like around our area as kind of just big clumps of zillions of individual clay mineral grains. So I'm going to show you a picture of some of the micas, the Biotite Mica and the Here's a picture of the 2 micas. We have the Muscovite Mica over here on the left, and the dark one is the Biotite Mica. it tends to be dark brown to black in color, so you might remember B, biotite. B, it's the brown one or the dark one, brown to black one. And which of the two do you think is mafic silicate? The one that has the dark color, right? The biotite mica. But they're pretty similar in their shape. They have this kind of peculiar shape. They come in these very, very thin sheets, and it's real easy to peel the sheets of Muscovite mica apart, and the sheets are flexible. The biotite mica is a little harder. It tends to flake off instead of coming off, apart in nice sheets. But both the micas have that characteristic sheet-like shape or habit because they're sheet silicate minerals, right? The bonding within the sheets is bonding between silicon and oxygen within the tetrahedra, and it's very strong, and that helps the minerals grow into these sheet-like shapes. And then the sheets separate because the minerals both have excellent cleavage parallel to the sheets in that one direction where those bridging cations that are more weakly bonded are. So the micas are very common really in all types of rocks, so we'll see those in the igneous, sedimentary, and metamorphic rocks during the semester. I just wanted to return to this drawing to say that this is the last silicate mineral group structure that we'll sketch out, because the next group are the framework silicates. And the framework silicates have this fourth oxygen that's above the plane of the blackboard, or the plane of the screen rather, also shared with another tetrahedron. So there's a whole other layer of tetrahedra directly attached to the tetrahedra that you see in the slide. So there's this three-dimensional framework of tetrahedra that really I don't know how to draw, so we'll just discuss that in the module. I think most of it's on the next page in the module.